Hello, Elena.
Hi.
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 Yeah.
Hello.
Hello. Moncy will arrive shortly, I guess. This will come.
Hi. Hello.
Elena, have you checked YouTube? Is it working fine?
I haven't taken a look at it now.
Ah, yeah. You just. What I checked, it's working fine, but I guess you can also check.
So yeah, I guess it's working fine.
Yeah. Nice. Yeah. Nice. So in 3 minutes, we will start. Yeah. So I guess Robert can start. Robert, if you would like, please come in our meeting. Yeah. Yeah.
Okay. Perfect. So, thank you for attending this meeting. I think we have So
to calculate the transfer of linear momentum from this galaxy onto the small dark matter particles. So essentially the dark matter halo of the host galaxy absorbs the kinetic energy of the incoming satellite. This is known, calculable through this type of formula here. This is the Chandrasekhar dynamical friction. And you note, so the deceleration here of this velocity depends on the velocity of the satellite cubed, 1 over the satellite velocity cubed, times then all these parameters here. So it's actually 1 divided by velocity squared, because we have here the quantity of the velocity 2. And then it's also proportional to the mass density of the dark matter halo. So this m is the mass of the dark matter particles here, and rho 0 is the number density. So this quantity here is fixed by the model, by the CMB, essentially Big Bang model, so by the Lambda-CDM model, which is fit to the CMB properties. And so this is not a free parameter one can choose. So this test is insensitive to the mass of the particles. It's only sensitive to the mass density of the dark matter, fixed by the model. There seems to be some echo, and so we have now the situation of the satellite galaxy creates this wake and then decelerates, and therefore it falls towards the center rather than being on a hyperbolic flyby, which we would have if there were no dark matter. And so we can now test whether the flyby velocities are small, given this effect of deceleration through this dynamical friction. And this is why galaxies merge, but only in the dark matter theory, because if we have a theory without dark matter, they would typically fly past each other on hyperbolic orbits. And here's an example of two galaxies merging, which you can see how quickly they merge. It's basically within a crossing time. And so this Chandrasekhar dynamical friction is very well understood, and we can apply this now explicitly. Here's just one test which was applied by Gary Angus et al. In the year 2011 already. So we have here from the theory of Lambda-CDM structure formation, the mass of the galaxy. For example, our Milky Way would be around 10 to the 11, somewhere up here in stars and gas. And the dark matter halo mass of this galaxy is on this axis. So our galaxy would have a dark matter halo mass of a few times 10 to the 12 solar masses, somewhere up on this end, according to the theory. Now, we can't vary this at will at all. There's a small range of variation, simply because each galaxy has a different merger history, but we cannot change this number, this correlation between the baryonic mass and the dark matter halos as we wish. Okay, that is fixed by the theory. Up to this variation, each of these points is a galaxy formed in one of these simulations, which are listed here. And so if you look at the satellite galaxies here of the Milky Way, we know their distances from our galactic center, we know their velocity vectors, and we know their luminosities. And so the luminosity reflects the baryonic mass of these objects, which is below about 2 times 10 to the 6 for these here. And therefore, the dark matter halos these satellites are allowed to have are confined to this region here. However, now, this is the condition that we have our Milky Way and the satellite comes in the theory, and it will not be allowed to be on hyperbolic orbit, so it would fly away because it must be stuck, because it has to become a satellite, so it must get stuck. So we can calculate by dynamical friction which dark matter halo do I need to get these satellite galaxies stuck in the Milky Way so that they don't fly out again. And that means we need this dark matter halo for each of these for them to get stuck. Otherwise, they wouldn't be on these type of orbits and they would be receding from the Milky Way. While the fact that they have these dark matter halo masses we are forced by the theory to be in this regime. And so this regime, these two are incompatible. So in order for them to get stuck, I need a much more massive dark matter halo than the theory is allowed to give me for that mass of the satellite, right? And so this basically tells us that there's no in-full solution for them to get stuck given their observed properties, and therefore they can't be dark matter halos. So that's one test. And of course, we can look at a large imaginary cloud and small imaginary cloud. Here we have the imaginary extreme, that's the Milky Way, and calculate their orbits, assuming they are dark matter halos. Now, the calculations, which are in this upcoming publication, we can see that, so this here is the gravitational attraction if the LMC is away from the SMC at 10 kiloparsecs. And this here is the dynamical friction force of the LMC on the SMC and SMC on the LMC, because they are both in the dark matter halos of their own dark matter halos, and these two dark matter halos are inserted in the dark matter halo of our Milky Way. And you can see that the gravitational attraction between these two galaxies and the dynamical friction force are comparable, in scale. This precludes orbital solutions. So no orbital solutions, because the LMC and SMC would just merge far too quickly. Now, again, that rules out the existence of dark matter halos. And then we have these nice tests here on the bars of the galaxy. So a bar of a galaxy is rotating in the dark matter halo of the galaxy, and the dark matter halo therefore absorbs through the torquing the angular momentum of the bar, so the bar should get slower and then shrink in length. And that is not seen as this detailed analysis shows. This is a more than 5 sigma disagreement between the dark matter models and the observed galaxies concerning these bars. And then another test by these 3 publications tells us that this group of M81 with its fairly major satellite or companion galaxies would merge within 1 billion years, but we need significantly more than 1 billion years to produce all these gaseous streams through encounters. And so again, this existence of this system does not allow them to be in dark matter halos, because the dynamical friction of all of these in their dark matter halos is just immense, so that the whole thing should be merging within about 1 billion years, which is not observed. And so there's no dark matter, and therefore we must use a different law of gravitation. Okay, so this existence for dark matter test is independent of any idea of an alternative theory of gravitation or of MOND or so. But since there is no dark matter, then we must therefore change the law of gravitation. So different than Newtonian dynamics of gravitation. And here we are at the currently testing MOND, and here one could argue, first of all, going back historically, how was the current understanding of gravitation developed? It's based on the work of Newton in the 17th century, who took the data from the solar system, inner solar system mostly, and then Einstein in 1916 reformulated this in terms of a space-time distortion, but still solar system data, because at the time of Einstein, galaxies had not been mapped out. They were not understood what galaxies were, so Einstein had no chance to improve the law of gravitation beyond the reformulation as a space-time curvature. And so I think I'm running out of time, right? You want only 10 minutes?
Yes, one minute more, please.
Yeah, then... well, then I will not get to the tidal test. It's okay. This is an important Gedanken experiment, which actually goes back to Indra Banik. And so we have here the trampoline. And if you put weights on the trampoline, so heavy weight gives a larger depth. Depth goes up, so the depth will be larger. A smaller weight, smaller depth, and smallest weight, small depth. We can then call this our law. Extrapolate it. Will it work? It won't work, because at some very small weight, of course, the fabric, the material structure of this will play a role, right? And so this empirical law here breaks down at very small weights. And basically that's what we are saying, and that's what MOND is telling us, that when we go to space-time curvature, which is extremely small, additional effects seem to play a role, and that is encapsulated by the formulation of MOND. And just as a brief, I'll just skip through to the final slide here then. So the tidal tails of star clusters, so stars leave the star clusters through tidal tails. And in Newtonian gravitation, the number of stars is symmetrical, same here as there. In Newton, we have more here, and that is indeed observed, right? So this actually tells us that MOND works on these parsec scales and correctly predicts the overabundance of stars ahead of the leading motion of the cluster compared to the back. So I think I'll end here then.
Okay, thank you. Thank you very much for the very interesting exposition. We can continue with the discussion, and we have a few questions collected from the last weeks, and maybe also for the in live from the attendees. The first set of questions is about the paradigm shift. For example, for the question related to this issue, I am reading now. Does the recent discovery done by James Webb Telescope prove that the Lambda-CDM model needs to be updated or completely rejected? I think is most answer, but you can comment something. Other similar question is, as a whole, cosmology is in such a state of despair seems like there might be underlying more than fundamental assumption that needs abandoned. Do you think that it's possible to revision of only a fundamental assumption could be resolved most of the problem of cosmology? Are the first principal alternatives to Lambda-CDM with no additional free parameters? And the last question related to the paradigm shift is, one could also ask whether there are any alternative way to think about the universe other than Lambda-CDM. What are the alternatives for this?
Well, so I wrote down some answers into the sheet, right? And those are all very deep, very important questions, and that's what we are, of course, working on. So the JWST observations currently, as far as we know, they do indicate that the galaxies between a redshift of 10 and 20 are far too massive compared to Lambda-CDM. And so, yes, that is yet another stress point for the theory. One could envision that a top-heavy IMF might partially alleviate the problem, because then the galaxies are less massive and they send out more light. And if you assume the stellar IMF is invariant, then one would infer them to be too massive. In fact, if the galaxies have a top-heavy IMF, then for the same light we get less mass. So that is a possibility, but this doesn't really work, I think, but it hasn't been fully calculated, because the structure formation with a varying IMF would be different, because the feedback would then be stronger, and so it will actually be harder to form more massive galaxies because of the stronger feedback, right? At low metallicities, if the IMF becomes top-heavy. So yes, it seems that the JWST observations are indeed another nail in the already closed coffin of Lambda-CDM. I mean, you can keep on adding nails into that, as you can spend the rest of your life hitting nails into that coffin. But it's and that's what these other questions are now indicating. We need to go away from that coffin, put it into the ground, and start thinking about a completely new theory, right? And from what we are doing here in Bonn, in Prague, St. Andrews, and Nanjing, is to base our work on MOND, because MOND has an incredible track record. In fact, to my understanding, MOND is the one theoretical description of gravitation which offers the greatest number of predictions which have been verified. And this goes from gigaparsec scales, surprisingly. I mean, in MOND, we don't have a Hubble tension. In a MOND cosmological model, we don't have a Hubble tension, so this is one aspect. And down to star cluster scales and even into the solar system, where we see the Kuiper belt objects having in a MOND-like. Then there's the wide binary test, which of course is an issue now, thanks to Indranil. Thanks, Indranil, who's connected. But yes, the overall, I think MOND seems to be the current correct direction, and so that's what we're investigating. And the cosmological models we are building based on MOND, so no dark matter, appear very, very promising.
Thank you for the answer. Questions from the attendees? At the moment, it's not ice breaking.
One question in chat, I guess somebody has asked.
So what is the explanation for the bullet cluster and similar observations in Milgromian MOND gravity? So that's the terrain of Elena, of course. But don't know, Elena, do you want to say something to this, or shall I continue monologuizing?
Whatever you prefer. If you like to say the question, that's fine.
I can give my way of answering it, and that is just to say that this was one of the greatest PR gags by the dark matter community, and PR gags are always dangerous. It's so in Milgromian gravitation, it works in the sense that we get the velocities and the timescales right, and the fact that we even have these massive clusters. El Gordo, that's Elena's specialty in particular, actually works fine in Milgromian gravitation in terms of building the clusters and having them collide, pass through each other with the observed velocities. I mean, with the deduced velocities. There's a slight tension with the mass in the clusters, which, however, depends on how one calculates the masses of the clusters, right? And that then is an issue of what tracer do you use. Do you use weak lensing? Yes, maybe that's a good way, but weak lensing in which theoretical framework? In Einsteinian gravity? No, because that's been ruled out. So you have to do weak lensing analysis in a MOND relativistic theory. Has anybody done that? No. So therefore, that particular way of arguing that Milgromian gravity would be not compatible with bullet clusters is stupid, basically, because you have to be consistent in the theory you're using. And so the work we have done, especially now based on what Elena has been doing, clearly shows that bullet cluster and the El Gordo cluster work well in MOND up to the point that maybe there is some tension with the mass in these clusters.
Thank you very much. Maybe more questions, typing or raising hand. No, by the moment.
I would like to ask one question. If people are also speculating about varying the fundamental constant, like Newton's gravitational constant, Planck constant. So, is it making some sense, or like, does this help anything to alleviate some tension?
Well, it makes a lot of sense to inquire whether these fundamental constants are changing, because they might be or they must be coupled to the properties of the vacuum, and the properties of the vacuum are obviously, apparently changing since it's evolving. So I think that's a very important aspect of this whole game. But for that we need some empirical evidence. I think, and currently there is no empirical evidence for any variation of these constants as far as we can tell. So what we are doing here in this grouping in Bonn, St. Andrews, Prague, and Nanjing is to assume these constants are constant, and see how far we get with that. I think Srikant has a question. Yeah, maybe.
Yes, Srikant.
Yeah, hi, hello. Thank you for a nice talk.
Srikant, can you unmute your YouTube?
So the question that I have is, so sorry, there is some noise. I'm hearing back my voice again.
Yeah.
There's some echo.
We don't hear the echo. At least I don't hear it.
Yeah, I hear an echo, but now it's okay. It's done. Yeah, and now I can. Now I can speak. So my question is, how is MOND doing with the cosmological observations? Because I hear like some conflicting views in some papers, saying that okay, MOND is not in good agreement with the standard cosmological scenarios, or like in some dark matter observations. Because I'm not a person who works on MOND, so maybe how do you address?
Well, let me say it this way.
Yeah.
Yes, MOND is in total disagreement with the dark matter model, and that's because the dark matter model is in total disagreement with the data. Right? So MOND is, as far as we have been testing, from gigaparsec scales down to the parsec scale, in excellent agreement with the data. There are some issues which still have to be resolved, and that is concerning the mass of galaxy clusters, which might indicate the evidence of a stellar neutrino. That could be the case. But as I'm saying, we need to understand what these masses of galaxy clusters mean in terms of the measurement, because the galaxy clusters are the largest structures which are visualized, partially visualized. Many of them might not even be visualized. They might not be in thermodynamic equilibrium. They're still in the process of formation. The boundary conditions are not well understood since these things are in the process of formation. They're still assembling. And so deducing from a galaxy cluster by this factor of 2 mismatch, which is currently being discussed, is ludicrous given all the other evidence how MOND does so excellently. And then the only other tension is the wide binary test. Thank you again, Indranil, for who's published a paper arguing that it doesn't work. And there again, there are two teams claiming it does work. So MOND does extremely well. Newton is totally ruled out. Indranil found in his analysis, very, very large analysis, that MOND does not match the data, and we are in the process of trying to understand that particular issue. And the solar system, it seems to, MOND again seems to work, but in MOND is currently, it's a large framework, right? So you can use a particular formulation. I have it in the slides, but I didn't show it. You can use the Aqual formulation, which basically generalizes the Poisson equation in a very elegant manner, or you can use a QMOND version, which is a more not so nice way of writing down effectively MOND. The Lagrangians differ for these. There are subtle differences, especially in the transition region, when you go from the deep MOND limit to the Newtonian limit between these formulations. Then it's possible that MOND might be a modified inertia theory, which is an extremely theoretically very hard to formulation. Which is very difficult to put into a computer. And at the end of the day, what we can only do is, in order to compare with the observational data, is to have equations of motion we can code, right? And so we are forced at the moment to use basically Aqual or QMOND formulations, and they work as well as one can imagine any theory to work, given all these uncertainties, even in the data, right? So,
perfect. Thank you.
Thank you. Thank you.
Okay, it's fine. Perfect. Another question is from Tom.
Hello, Tom. Nice to see you.
Hi, Pavel. How are you? The question is, what is your current explanation for the acoustic peaks in the cosmic microwave background?
It's a good question. I have never in detail studied that. And I was just going to say, based on some of these questions in this spreadsheet, so there were some deep questions about a completely different model related to inflation, dark energy. And that's basically what this is about, right? So can we... So there's one way to doing a MOND cosmology, which has been goes back to Gary Angus and has been investigated by Katz et al. And then now most recently by Wittenberg et al. Here in Bonn and St. Andrews, where we assume that the Lambda-CDM expansion history is the same. So we have an inflation epoch. The CMB is the same as in the standard model. So the surface of last scattering and so there, these peaks are the same. They have the same interpretation as in the standard model.
So that's dark matter.
So basically, in that, so that's the new HDM cosmological model, which has stellar neutrinos in abundance, as the Lambda-CDM model has in cold dark matter, which is a hot dark matter component. But the attractive aspect of that is that stellar neutrinos are less exotic than dark matter, than the cold dark matter particles, because the stellar neutrinos can be are more closely associated with the standard model of particle physics, right? Because you've got those three active neutrinos, which apparently change their masses as they propagate, and so there's a theoretical argument to say that there must be a fourth inactive neutrino version. That would be the stellar neutrino, and things seem to work out quite well in terms of the abundance of the stellar neutrino, the galaxy cluster mass mismatch. So Indra can actually say more to this than I, but this is a very attractive approach, and that would account for these for the properties of the CMB. However, that model seems to form structures too late and maybe form too massive structures at late times. Yeah, so there is some tension which is now being investigated, particularly also in St. Andrews. And so I'm taking this as a motivation to depart even entirely from that, to discard inflation, dark energy, and reinterpret the CMB to be something completely different.
Yeah, so I looked at neutrinos, HDM, for instance, and the fit isn't quite as good as Lambda-CDM. You could say it's rejected, but it's close enough that it's encouraging. What I actually did was think about magnetic seed fields in the early universe rather than MOND, but I mean, the point is the CMB does need some sort of dark matter, so you're just arguing against it on small scales, but on large scales you're accepting it, are you not?
Well, in the new HDM model, the stellar neutrinos would take that role, but it's a hot dark matter component, effectively. But we are now asking other questions. So in terms of a radically different cosmological model, I call it the Bohemian model of cosmology. I don't at this stage want to give the details because it's being written up now. But that model gets rid of basically everything which is in the standard cosmological model, right? And that is a viable way to go too. But it hasn't been published yet, so I'm not confident at all that the CMB is what people think it is in terms of the surface of last scattering, because there's an asymmetry, there are issues with the properties of the CMB. Any model I know of which has been using the CMB as a boundary condition to calculate structure formation leads to a model universe which does not agree with the observations. So I have to change the boundary conditions, or I can think about changing the boundary conditions.
Okay.
Thank you. Thank you very much. So now is time for moving the next talk from Elena Asencio, also Bonn University. The talk is on current problems of Lambda-CDM on large scales, El Gordo galaxy cluster, and the KBC void. Whenever you want. Elena? You're mute.
Yeah, now you should be able to hear me.
Yes.
Okay, great. So hopefully you can also see my screen.
Yes.
So yeah, as Robert was saying, the talk is on the current problems from Lambda-CDM on large scales. So you probably have heard many times that Lambda-CDM explains the large scale structure so well, and it's such a successful theory on these scales and all that stuff. But actually, Lambda-CDM has many issues on large scales. So, for example, one of these cases in which Lambda-CDM has a problem is on explaining El Gordo galaxy cluster, a supermassive galaxy cluster at redshift of 0.87. Another example would be the KBC void, which is a very, very large void or underdense region between 40 and 300 megaparsecs around the local group. And of course, there is the very well-known Hubble tension that you have probably heard about. So to start with the first example, El Gordo is, as I was saying, a supermassive galaxy cluster at redshift of 0.87, formed by two subclusters, which have a total mass of 2.13 times 10 to the 15 solar masses. Now, this is a very, very large mass for Lambda-CDM expectations. So in Lambda-CDM, if you take a simulation and you ask the simulation at redshift about okay, give me the most massive extreme object that you can possibly find in the simulation. So the Lambda-CDM simulation would form objects of maximum 1.7 times 10 to the 15 solar masses at this redshift. So significantly lower than what we're seeing here. So that's kind of a problem for the theory. But the thing is that that's not where Lambda-CDM problems end regarding El Gordo, because El Gordo is also known for being one of the hottest, most X-ray luminous and brightest galaxy cluster at this redshift. And this implies that in order to make this very high temperature and very high luminosity, the two subclusters must have collided at a very, very high inflow velocity. So at about 3,000 kilometers per second, which is, again, a lot higher than what Lambda-CDM expects. So in Lambda-CDM, one would expect these objects to collide at maybe 1,000 kilometers per second or even less. So if you take into account the very high mass and the very high inflow velocity, you find that El Gordo is an object that is in more than 5 sigma tension with Lambda-CDM. It cannot possibly be explained by this paradigm. And then from this, one would perhaps deduce that in order to explain supermassive objects like El Gordo, structure formation would need to be more than CDM predicts. Now let's assume this statement is correct. If structure formation is more efficient than we expect, then the matter would aggregate into these supermassive structures easier, and therefore this would leave gaps or underdense regions where the matter used to be. And the funny thing is this, such underdense regions have indeed been observed. So a local underdensity has been observed in several wavelengths, so in optical, in radio and X-ray and near infrared. And among all these studies that are mentioned in here, the one from Keenan Barger Cowie of 2013 was the one that found stronger evidence for an underdensity. So what they did in their study was they sort of counted galaxies and they observed their distribution in the surveyed volume. And what they found in this study is that the density was about 0.5 times the cosmic mean, between 40 and 300 megaparsecs. So to be a bit more specific, the density in this very large region has a density contrast of 0.46 as observed. This is a lot higher than what Lambda-CDM predicts, because from Lambda-CDM we have the CMB constraint that tells us that the expected density fluctuations should only have an amplitude of 3.2%, so 0.032, like a lot smaller. So yeah, that's definitely another problem for Lambda-CDM. So maybe from this, maybe it's easy to see how the El Gordo problem and the KBC void problem are related, but then maybe you are wondering, what does this have to do with Hubble tension? So these problems are perhaps and probably related to the Hubble tension, because I don't know if you ever heard the possibility that the H0 anisotropy might be caused by bulk flows. Now, what is a bulk flow? So bulk flows originate when local matter inhomogeneities lead to a stronger gravitational pull from the underdense region towards the denser one. So the matter in the underdense region feels the gravitational pull of the denser region, and this makes it move towards the denser region. So this stronger gravitational pull would appear as if the universe was expanding at a different rate in the inhomogeneous region, and thus leading to the observed H0 anisotropy. So it looks like the universe is expanding at different rates, but it's just this pull from the underdense towards the denser region. And well, just to clarify, these bulk flows are not just a theoretical construct. These bulk flows have indeed been observed and studied in several studies. And as to whether the observed bulk flows matched the observed underdensity observed by Keenan, Park, and Coe. So the answer is, well, the answer was given in a very recent study, and well, it has previously been studied in Hasselbauer also. But very recent studies show that for Gaussian and exponential profiles, for the density, you can qualitatively match the bulk flow curves, which, yay, that works. So just to summarize, we have three main problems that I wanted to talk about today, which are El Gordo and the KBC void and the Hubble tension, which all seem to point to the fact that structure formation does not work like the standard model predicts. And well, I also wanted to mention that I focused on 3 cases because I just had 10 minutes and didn't want to run out of time, but there are like so many other things pointing to the same conclusion. Like, for example, one would see different star formation rate densities in local and global universe, or just to mention that El Gordo is not the only supermassive galaxy cluster that has been observed. Like, it's a problem for the ΛCDM. Like, there have been many other supermassive galaxy clusters that also have problems. There's also the fact that 1 gigaparsec arc of galaxies and galaxy clusters has been found at 0.8. That's also very hard to explain with the current model. And of course, as we were mentioning before on Pavel's session, the preliminary James Webb Space Telescope results also point to the fact that structure formation is a lot more efficient, because otherwise we could very hardly explain, or we could not explain, these very early and massive galaxies forming so close to the Big Bang, say, somehow. So yeah, that's all I want to say for today.
Thank you very much, Elena, for adjusting the time very well and very interesting talk. We have some comments from maybe and Tom also. They want to share. Speak Ranil, Tom.
No, I was just providing some information, but I just want to mention that, like, there's a more recent study by or discovery by Lopez of like a ring of galaxies at redshift 0.8, which is similar to what Eleanor's talking about. It's more recent. I think that hasn't yet been peer reviewed.
Yeah, actually, I was discussing it with Robert yesterday.
Yeah,
I mean, I didn't include it because I couldn't find the paper.
Yeah, I don't think it's been peer reviewed yet.
But yeah, I also saw that, and yeah, more problems.
Well, I think it's more of a sign that you need enhanced structure formation, probably. But it's the 2022 paper. I believe the methods used this time around are similar. It's worth looking into, like how. I mean, to analyze it statistically, you probably do something like quantify the length of the arc versus the redshift, and see in that 2D parameter space, like what's the expected distribution, how much of an outlier it is. I don't know if anyone's done anything like that.
I'm not aware of any studies.
Okay, thank you.
On that.
Thank you. So more questions by at the moment. I can't read the previous sent questions to the form. For example, do you think that is possible with only one fundamental assumption, the revision of one fundamental assumption could resolve most of the problem in cosmology, or we need several corrections of the fundamental principles?
So, well, in general, in my talk, I was making a strong point towards the fact that the main problem here is that structure formation is not efficient enough. So that could be seen as one thing, but it's not like one could easily solve that in the standard model. Like one cannot just say, okay, so now we make structure formation more efficient and everything is solved. Like you would really need to revise the whole paradigm, I think, in order to fix this problem in the standard model. So even though it looks like one problem, it would need a very complex solution within the standard model. So it's not just one thing, I would say.
Mm-hmm. And the alternatives is tested with the same observation to check if works well for the same issues.
So about alternative models, you mean?
Yes, the MOND and relativistic MOND or other modified theories.
So in general, I would say it's hard to answer these questions without having actual simulations. And up to now, the only detailed simulation that has been done in terms of MOND, which would be the alternative model, was the one with stellar neutrinos that Pavel was also commenting about. And one does see that with MOND, it's a lot easier to form these structures. So El Gordo or the bullet cluster or the supermassive clusters or the void itself, they are easy to form in this MOND plus neutrino cosmology. But as Pavel was also saying, it does seem that the neutrino, the stellar neutrino plus MOND model also has its own issues. So I think we still need to keep testing more models and see how that goes.
Okay. More questions here. I think is
some comments on chat, maybe. Yeah. Frederick.
Comments. Yes.
Maybe.
So, yes. Okay. Yes. So Frederick.
Yes. Maybe it's not a good question, but sorry if it's maybe it's a ridiculous question. But you told us, thank you for the presentation. You told us about simulations. Okay, so I understand. I think simulation of MOND and Lambda-CDM. And do we have also, apart from these simulations, equations? For example, I suppose in Newtonian, pure Newtonian regime, it would be a sinusoidal curve. I'm talking about the density curve, the resulting density curve, which should expect, for example, today in the different models. In the Newtonian model, probably, I don't know exactly. Probably there is something like a sinusoidal curve which describes the density distribution of today. In MOND, maybe it's different. In Lambda-CDM also. Okay, in surrounding, maybe I can talk about something. I have a very exact equation for that. So that's why I asked you questions. Thank you.
So I don't know if I fully got the question, but I mean, as to whether we have the equations. I mean, like I said, I do think it's hard to give a clear answer without simulations, because in order to form these objects, you need to take a lot of things into account, like for example, for the simulations that have been used for Lambda-CDM or the neutrino MOND simulations, you always start with a background cosmology, usually given by the CMB, and this will give you how the systems will evolve and how they affect each other. So I think it's a very complex problem. So of course, the theoretical equations or just the math can give you some insights, but I think it's hard to know unless you do the actual simulation. But yeah.
Okay, thank you. Yes, I think you understand very well my question. Thank you very much. Thank you for that. Okay.
Okay.
Maybe
I have.
Can I just add just a quick statement to Frederic, and that is that if you have a model which tells you the average density in the universe as it evolves, right? The observations can deviate from that if over and under densities form. So we can be in a major underdensity and see only a fraction of the matter around us that would otherwise in an analytical calculation be there. So this is something one has to take into account.
Okay, so it's not so simple. Thank you.
Yes, indeed, I think that also a clue, a key point is the most effective force of the MOND theories for low accelerations. With these more effective interactions, I think is evident that the structures grow faster than the standard gravity. Yes. Thank you. More.
Yes, thank you.
Not yet. Wait, more questions? Okay. So we can continue with the list of questions sent before.
One question to
yes.
I would like to. So one question was that can MOND or modified gravity correctly address the virial theorem in clusters? Like the virial theorem does change in MOND type of gravity, or it remains same? Anything related to virial theorem? Like
so I mean, yeah, the virial theorem does look different in MOND in the sense that the equations change. But are you referring specifically to this paper that talk about this, or is that general question?
Yeah, it's just a general question, like for MOND type of gravity, like what are the changes we see?
Yeah, I mean, like when you introduce a different equation for gravity, of course your equations are going to change.
Okay.
But yeah, I mean, as far as I'm concerned, this is something that works.
May I comment?
Yes.
Yes.
So I mean, like Indranil was saying, like the concept is the same, but of course the potential energy will change because your equations have changed in terms of the gravity.
Yeah. Asser wants to say something.
Yes. You see, the virial theorem depends on Newton's third law. And if you take into account retardation, Newton's third law does not hold. That's obvious. And therefore, you need to put some correction to the virial theorem if you intend to use it on the scale that people use it. I mean, on scales of a galaxy cluster, which is a few megaparsecs.
Can I address this? Is that okay?
Yes.
Yes. So the retardation effects cannot really be very, very significant because, for example, when the Earth's orbiting the Sun, the position it sees the Sun is sort of delayed by 8 minutes, or they're retarded by 8 minutes. Now, if the force of gravity on the Earth due to the Sun was towards where we currently see the Sun, as opposed to where the Sun sort of instantaneously is, then the Earth would spiral into the Sun in only a few thousand years. So it's sort of understood by now that basically what happens, the Sun sort of depresses the space-time fabric, if you like, or distorts it. And this obviously happened sort of billions of years ago, and it's created a steady state pattern in the fabric of space-time. And the Earth is like a test particle moving in that, right? So at any moment in time, the gravity on the Earth is towards the instantaneous location of the Sun, rather than where we see the Sun on the sky. So because of this, the retardation effects of course, would, if they existed, would in principle be more significant in a galaxy cluster. But we already know that that's kind of not how things work, essentially.
Well, I can respond to this by saying that you are correct regarding the solar system. And if you read perhaps my paper on Mercury, you would have seen that. But it's not true on every scale. The solar system is so minute with respect to galaxies and galaxy clusters that it's a totally different scale. And things are affected differently on different scales because of retardation.
Thank you.
Okay. More questions
in
the chat? Yes.
I have one question, if
Yes,
you allow me.
Of course.
What do you think about universe linearly expanding at the speed of light? I mean, the Hubble horizon coincident with the Hubble radius coincident with the horizon.
Yes, I think it's a question for the second session.
I think Robert and the others will address specifically this in the next session. So maybe it's better if...
Yes.
I wanted to know your opinion, simply.
Oh, my
your opinion, Elena. Okay.
Okay. No, I mean, it's... I think it's a very striking coincidence how well the data matches the expectations for a linear expansion. Like it's a very surprising coincidence, I would say. But yeah, like and to be fair, I'm not a cosmologist, so I don't know what's exactly going on. But yeah, I mean, I do think it's something that it's interesting to look up in more detail, and that yeah, definitely a possibility, I would say.
Thank you, Elena.
Perfect. Yes, I think the idea is to solve gravity for all scales, for galaxies and the cosmological scale, without the use of dark matter and dark energy. So the linear expansion is one of the possible solutions that are compatible with MOND, and it's possible to work with dark matter in both scales. I think so, but we will go into detail in the second session. If no more questions, yes, more questions, no? Okay, if no more questions, we can advance for the second session. That is about the modified gravities and modified cosmology. This is moderated by Elena Asencio. So please take your word whenever you want.
Okay, so welcome everyone to the second session on modified cosmology and gravity theories. So first speaker of the session is Saddam Leonardo Kap from the Indian Institute of Technology in Kanpur, India. So Saddam, whenever you want. I think you're muted, or maybe you're just not speaking.
Is my screen is visible?
Yeah, your screen is visible.
Yeah. Thank you everyone. My title of talk is Modifying the Standard Lambda-CDM, a non-minimal coupling between dark matter and K-essence scalar field. So the talk would be more theoretical. So first of all, we start writing an action for this non-minimal coupling feature between dark matter and some scalar field which is driving this cosmic acceleration. So first term we are having the first term with the Ricci scalar R is Einstein-Hilbert action, and in second one we have a dark matter fluid model given by Brown. It's action for the perfect fluid, And you can see over here that there is a rho, which denotes the energy density of the fluid, and it's a function of number density and entropy density. And we have this J mu, the flux density, which is contracting with some Lagrange multipliers, this phi, s, theta, beta, and alpha. So these are Lagrange multipliers, and these commas are actually giving the space-time derivative, a covariant derivative over here. And because these are scalar, then it becomes simply partial derivatives. So these Lagrange multiplier, we can have some physical, meaning. For example, this theta becomes the gradient of temperature. Similarly, we have phi, it becomes gradient of potential, and we have this entropy. On the other hand, we have alpha, which shows that the Lagrange fluid coordinates. Then we have some K-sense Lagrangian, which depending on some field, that is a phi, and the kinetic term, which is actually half phi dot square. And for the K-sense field, the Lagrangian have some non-canonical type of structure because its potential is multiplying with kinetic term, and this kinetic term has some x and its higher power, so minus x plus x square. And so if we are taking this action up to over here, then this matter, the dark matter and the scalar field are minimally coupled to gravity. So now we are adding some different interaction type of Lagrangian, which makes this whole system as a non-minimally coupled. And therefore, we are introducing the interaction like this. So we can have some interaction function that depends on the number density, the entropy per particle, entropy density per particle, the field phi, and its kinetic component. So it's actually showing that some interaction is going on between the dark matter and about the scalar field, which is actually candidate for dark energy, and they are always minimally coupled with the gravity. So it's some kind of non-minimal effects between the matter fields. On the other hand, we can also introduce something so that this action is remain a scalar quantity, which is so interaction function f, and then there is a particle flux density is contracting with the field velocity j mu d mu phi. So we are introducing it. Maybe it can give us some nonlinear behavior during the matter epoch, and it may have some deviation from the Lambda-CDM standard model of cosmology. On the other hand, we have a different scenario where the interaction function is multiplying with Ricci scalar in that way that we have modified the matter sector, but at the same time, there is the modification that takes place in the matter sector also induces some change in the curvature part. So such modifications has simultaneously change in both the gravitational sector as well as the matter sector. So these are some form of non-minimal coupling between the matter and the gravity part. So we have seen that what could be the effect of this L interaction in our system. Then we can see in that the Friedman equation changes because of with some additional term, which is as rho interaction, as well as the second Friedman equation changes because of this P interaction. So we have this rho for the dark matter fluid, rho phi for the K-sense fluid, so K-sense field, as well as the interaction term that is coming from this L interaction. On the other hand, we have also the field equations also modified. If you vary the action with respect to the field gets modified because of these interaction parameters. For example, f, we have several derivative terms and so on. And this first equation also provides constraint on this dark matter fluid, because if we are just dividing with respect to 3h squared, then we can have this omega m, the fractional fluid density. So the first equation will provide us with the constraint on the evolution of dark matter profiling. Now we can study the system's qualitative behavior, but in general we cannot study this. We have to introduce some model. So here we are introducing a kind of toy model in which the interaction depends on the energy density, some field phi, and the exponential to the power kinetic term. Now this kind of interaction has some all the parameters like epsilon, m, and beta. So our job is to first constrain this one. Therefore, we have chosen to use the dynamic system stability, since we are not explicitly working on any data. Now, since our system is non-minimally coupled, therefore we have to consider it as an whole system. So we have defined the equation of a state, which is defined as the ratio of pressure to the energy density. And for the quiescence field, we are considering the potential of the quiescence field to the inverse power to the power of phi square, inverse power law type of potential. And then we have the pressure, so the propagation of pressure in the field as well as in the fluid. So the CS squared is basically give us that what is the speed of pressure perturbations in this whole system. And it has to be always between 0 to 1. It's the causality limit. It cannot be negative. If it's negative, then the model is not producing a stable kind of solutions. So first of all, by using the dynamic system analysis, we are getting some critical points. And for those critical points where we have some finite interaction, we have found that the equation of a state becomes epsilon and m parameter dependent. And here we can see the behavior of those critical points, in which the green region shows the accelerating regime where omega total lies between -1 to -1/3. On the other hand, the blue region shows the phantom behavior where the equation of a state is crossing -1. So we see that when we are closer to epsilon to the power minus, let us say 0.1, 0.3 and so on, and very close to m negative, then we are having this acceleration close to -1. So this is constraining epsilon m. On the other hand, we are trying to see that if we are picking some parameters, then our model is stable at the background level or not. Therefore, we chose some point between epsilon m, and then we have constrained this beta, the other parameter of the interaction, as well as the potential parameters. And in the blue region, we are seeing some stability of the model, that if it is stable, then it lies on blue region. On the other hand, we have some certain conditions that if the universe is entering at the late time cosmic acceleration, then the field density must be dominating with the sound speed that it must be always positive. So this constraint is shown by this pale yellow region, on which we are constraining this beta and delta. So we have in that way for different epsilon and m, in such a way that our model is producing enough acceleration, as well as this fractional field density must be dominating in the late time era, as well as the sound speed must be in the perfect limit, in the positive limit. So now we have also seen some qualitative behavior. In the left, we are plotting the phase space of the system. The phase space is three-dimensional, where x and y is representing the field parameters. On the other hand, the z is capturing the interaction parameter. And here we are getting some kind of critical points: a1, a2, a3, a4, and 5. So a3 is some kind of phantom point, and in which the interaction vanishes. So some trajectory which is originating at some point in the phase space, ending up a3, but it is non-physical because sound speed at a3 becomes negative. So we cannot consider it as a significant critical point. On the other hand, when we are seeing that in the left portion, where the trajectories are originating but ending up with a5. So a5 is a critical point where we can see some acceleration or phantom kind of behavior. With that, the model is stable and all the trajectories are ending up at a5. So the qualitative behavior, we can see some parameters evolution from past to present and future. So here n is the logarithmic of scale factor, and the negative n is actually showing us the past epochs, where we have plotted the fractional field density. Sigma square denotes the matter fraction density. Omega total is equation of state of the system, and sound speed is the sound speed evolution. Now, when we are seeing at the past, we are seeing that the quiescent density is dominating in the past. It's actually a behavior of the quiescence that although it is minimally coupled or non-minimally coupled, it can mimic a radiation kind of characteristic. So you can see that in the past, when quiescence is dominating, the green line, which is showing that omega total is starting with 1/3, and at this point the sound speed is also 1/3. So it's kind of the quiescence has some inbuilt characteristic that it can mimic the radiation epoch. So as we are progressing towards current epoch, the red line, which is denoting the fluid density, the dark matter profile density, then it is dominating and over here in this region, the quiescent density is subdominant, and as we are progressing towards the present epoch, then again the case density dominates, and the dark matter profile gets diluted, and we are entering at the late time cosmic acceleration given by omega total is minus of 1. So this is it. Thank you. So we have taken just only a fluid model, so for interacting model for this one type of interaction. And I also noted that if you are choosing same type of interaction for this particular second type of interacting non-minimal coupling of effect, we are getting the same result. On the other hand, we have studied this kind of interaction where there is a curvature coupled type of interactions. We have studied with the quintessence, and it has some different result. So I think, can I finish? Thank you. You're muted. Yes. So if any questions.
Thank you. I keep forgetting that I'm muted. Thank you so much for the talk. And if you would like to now go to the questions part, I want to start with the question regarding your model. Like you're sort of proposing a modified version of the standard model.
Yes.
So I was wondering, how does this modification, or how does this new model address some of the main problems that Lambda-CDM has? What kind of effect would it have on these things?
Recently, people have shown that if you propose some interaction between dark matter and dark energy, then the Hubble tension apparently can be resolved. So in this case, we are actually seeing some kind of effect, although we have not studied with the data yet, but in our current study, we are going to study some things. So it is our model is feature more dynamical thing, and we don't know anything about dark matter and dark energy. So if the Einstein's gravity is correct and all this model that okay, maybe there exists dark matter and dark energy, then still we have more room to take consideration that there could be some kind of interaction. So we are just seeing that okay, if there could be some interaction and we can study from the action principle, then what could be the effect that we can see. We are not saying that our model it's like a toy model, but we have to we have to test with the data.
Okay. Thank you. So are there any questions about the talk, or?
Pavel is raising his hand.
It's not showing in my computer, but yeah, sure, Pavel, go for it.
Yeah, hello. Yeah, I'm not visible, am I? So the question I had, Saddam, was because you just mentioned that you need to test the model, right,
Yes.
against data. So one immediate test would be this test I mentioned on the existence of dark matter, right, with dynamical friction. So in order for your approach or the approach of investigating some coupling between dark matter and dark energy to be viable, one would have to show that this coupling eliminates or reduces this dynamical friction significantly. This is a very strong condition, I think.
Okay.
So, yeah, because otherwise if dark matter is just free particles, then it's ruled out by the non-existence of this Chandrasekhar dynamical friction.
All right.
So that is a strong.
Yeah, I will definitely see those papers and try to test these. Thank you so much.
Okay, so Indra also has a question or a comment.
Yeah, no, I had a question. So I guess like much of what you're talking about is at the background level, but regarding the growth of structures in the universe, do you think your model can address the kinds of observations that I was talking about regarding these very significant underdensity of a massive galaxy clusters at high redshift? Would you be able to address these things?
Yeah, we are definitely working on that on the cosmological level, and some paper written by Boehmer, they have also been taken same framework, and they have worked with the quintessence, and they have shown that the structure formation is consistent with this approach, non-minimal coupling approach. But we have not yet tested with k-essence or maybe some version of other field. But I think it definitely will, because we have a general structure, and maybe some form of interaction can cope up with with this cosmological perturbations data. And it's,
so you might be able to enhance the growth of perturbations.
Yes, it may be, depending on the model.
Depending on the model. Thank you.
Yeah.
Thank you. So Ashir also has a question.
Yes, thank you. Now, we have a problem, right? We have in cosmological theory two unconfirmed ingredients, which are dark matter and dark energy. And I suppose most people here don't believe in dark matter.
Yeah.
So, but what you are suggesting is to replace those unconfirmed components with an unconfirmed field, which looks very much ad hoc. So can you comment on that?
Yeah, we have the evidence that scalar fields may exist because we have Higgs field and Higgs is a scalar field. So on that basis, and also we have inflation, right? That if we have a scalar field and a scalar field can mitigate the inflationary epoch in the early universe. So these are some motivations where, although these are very ad hoc term, but again, there are a lot of different cosmological data which are actually work with this quintessence model as well as k-sense model, maybe some ghost models. So yet we don't have a concrete proof, but it's the way we are actually progressing that for unknowns we can parameterize things and we try to see what happens.
Thank you.
Yeah. Thank
you. And Roberto also has a question.
Yes, a few. And this method of non-minimal covering could be also applied for relativistic MOND theories, Saddam, like the vector
actually,
and
yeah.
tensor. Yes.
Yeah, actually, I haven't yet started with MOND, but maybe if we have some specialist on MOND, so maybe they can comment that can we have some junction between this non-minimal feature or maybe MOND. I have not yet worked with this scenario, so maybe.
Mm-hmm. Okay, thank you.
So Frederick also has a question.
Yes, excuse me. Thank you for the presentation. I have a small question. If I understood well, it's algebraic work only. Is there any physical motivation for this algebraic work? We are talking about phi. What is phi physically, for example? Okay, that's my question.
The motivation comes from this Hubble tension, that we have ongoing Hubble tension and maybe some problems with structure formation and so on. That's why we introduce this non-minimal coupling effect, and people have also studied some different feature to address those things. So our ways are again an alternative that can we have this type of framework that can address these ongoing problems in current cosmology. Hubble tension is one of them, and also maybe some related with structure formation and so on.
Okay, thank you.
Yes. Yeah.
Mm-hmm. So Indri also has something to say.
Yeah, I had a quick question. Do you have what's the estimated age of the universe in your model? Because there's some constraints from stellar ages and globular clusters, right? Not really dependent on cosmology.
Yeah, we have not tested yet with. We have just studied analytically. We have not tested with the data. So.
No, but analytically, you can calculate the age or.
Yeah. Actually, yeah, we can calculate, yes. But we haven't yet done it, so I cannot.
Okay, fair enough. Yeah. That's something to look at, because I think you need about more than 13 and a half gig a year to make it work.
Yes. Yeah, definitely.
Okay. I think there were some other questions in the chat, maybe.
Yes.
Mm-hmm. So are there any more questions? Pavel also has a question.
There was one from K Indulekha in the chat.
Oh, in the chat you mean? Okay,
Yeah.
we can also address that. So, well, Pavel, if you would like to ask first, and then we'll look at the chat.
I would just want to make a sort of general statement on constructing models, right? So at least I can explain the way I tend to work, and that is that I taking the evidence. So that dark matter is ruled out by the absence of the dynamical friction effect on various different tests. It's not just that one satellite test, but the bars and so on. This means that if I then want to construct an alternative model, it cannot be based on dark matter unless I can show that it nullifies this dynamical friction problem, right? And at the same time, the evidence is telling me that with MOND, I can solve the Hubble tension basically trivially because that type of gravitational formulation, which is not ad hoc because it's basically it's already gauged on the rotation curves of galaxies, but applied to large scales, it forms these density structures which we see like El Gordo, KBC void, and solves the Hubble tension. So this is a strong indication that that's the direction to go. And so if one was to construct an alternative model, one would have to, on the one hand side, first demonstrate that it leads to the reduction of transical dynamical friction on dark matter halos, if there are dark matter halos in that model. And secondly, that it effectively leads to equations of motion which are Mondian. So through some coupling, say in the dark sector, but that those are strong conditions which today we have to fulfill. I just want to say that in general, that this, I think, should be done rather than just, I mean, there are very strong constraints these days on any alternative model. We are not free to try any particular coupling. You have to demonstrate at least these two facts about your or properties of any alternative model.
Yeah. So it's more like effective field theory approach.
Yes, but you have to demonstrate. As I said, you have to have these two conditions.
Okay. Yes.
Yeah, so I mean, it's okay to suggest a model, say in a publication, but then in the next publication you should address these two issues. So, for example, if we are now developing a completely new model of cosmology, call it the Bohemian model of cosmology, it is necessary for us to also take into account the boundary conditions which is given by the observed CMB, which doesn't mean that the observed CMB has to be exactly what everybody else is saying, that it's the photosphere of the hot Big Bang, but ACMB has to be produced in the model. It might have a completely different physical origin, but it must be there, right? Because that's what we observe. So just as an comparison in the issues.
Yes, thank you.
Yeah. Yeah, thank you. So maybe regarding the questions in the chat.
One from YouTube.
Mm-hmm.
Would the enhancement of structure growth on small scales like galaxy cluster also solve the cosmic sigma 8 tension? Is there is more power hidden in the small scale structures?
Would the enhancement of structure growth on smaller scales like galaxy clusters also solve the cosmic sigma 8 tension? Is there more power?
Daniel has an opinion also.
Yes, maybe.
Daniel
or
Elena?
Would anyone like to address that question, or?
Which question is that again? Can you?
It's about the SH tension.
The what?
Would the enhancement of structure growth on smaller scales like galaxy cluster also solve the cosmic sigma 8 tension? That is there more power hidden in a small scale structure?
Yeah, so I can say something. So this actually originally goes back to Moritz Hasselbauer, who's some years ago suggested that in the MOND cosmological models, we see these voids developing and then these overdensities, and in the voids there's just less matter, and then that has less fluctuations. And Indra also pointed this out in a comment. This hasn't been actually quantified yet, right? But I think that's a very promising ansatz, and it makes a lot of it's intuition basically, right? The model is intuitively doing the right thing, but it has to be quantified. So I think the sigma 8 tension is not particularly severe thing. It's not something I would say, oh, I have no clue how to solve that. I think it's an automatic, it probably find an automatic solution, just like the Hubble tension is automatically solved because of the voids.
Okay. And just to comment, this SH tension or sigma 8 tension has been found in the very, very local universe. So it would be consistent with the fact that we're in an underdense region. So I mean,
yeah, this is essentially what I was getting at. I think that's reasonable. This hasn't been quantified in detail how exactly it would work, but I think it's a reasonable thing to say.
Mm-hmm. Yeah, I mean that it has been studied up to, I think, 12 co-moving gigaparsecs, I think, or something like that. So like very local, and the void would be maybe up to 300 megaparsecs.
So the sigma 8 is generally only calculated up, I mean, okay, so in principle, your weak lensing probes any mass density along the line of sight. But as far as I understand, the technique is most sensitive to objects which are like halfway between us and the source is typically on redshift 1. So roughly speaking, you're most sensitive to like maximum redshift half, but probably less, maybe 0.3 or less. So yes, it is true that if we were in a local underdensity, that would reduce the S8, which is actually, say, 8 times square root of omega m. So yes, I think it's quite possible that if you're in underdensity, the locally measured value of S8 will not be the same as like if you were in an average density region or in an overdensity. That's possible. But I would agree with what Pavel was saying, though. The S8 tension is not yet statistically significant for Lambda-CDM.
Yeah, thank you. Any more questions, or should we?
Yeah, maybe we could move on to the next talk. So next talk is by Robert Monjo from the Complutense University of Madrid in Spain, and he's going to be talking about coasting cosmologies, and his talk is called Beyond the Standard Model: From Coasting Cosmology to MOND-like Gravities. So Robert, whenever you want.
Thank you, Elena. Okay. Can you see my screen?
Mm-hmm. Yes.
Perfect. Yes, as mentioned by Elena, this is an attempt to be beyond the standard model and show some clues about the linear expansion or coasting cosmology that Moncy John will explain later, and the MOND-like gravities as mentioned before. The idea is to check the principles of the cosmology, to review the most important base of this standard cosmology. As you know, we have a lot of problems, like the Hubble tension, the nature of dark matter and dark energy is not well explained by a standard model, and we need to introduce new parameters for explaining this tension, like the early dark energy or the dynamical dark energy, and more and more parameters to solve all the current issues of the standard model, like the overfitting of the epicycles for the well-known Ptolemeu model in astrophysics. So I am putting the attention to the synchronicity problem, that the age of the universe is very close to the Hubble time, with statistical compatible in most observation, maybe Planck with some tension, and the coincidence that the expansion now is very approximately to the one universe without energy, without matter. So empty universe and our universe are expanding in a similar way. The question is why? Why we have these coincidences? Also, all the observation seems to point that universe is flat, and a lot of observational issues, as mentioned before, but also theoretical issues, the flatness problem, the horizon problem, the infinity problem. Can a singularity expand to an infinite flat in an finite time? For a finite speed, like the light speed? And one interesting theoretical issue is the embedding problem. Why is separately embedded the spatial section and the factor scale? That is, my concern is that the Feynman-Lemaitre-Robertson-Walker metric is artificially built with two steps. First, the spatial part is statically embedded in a spatial Riemannian spatial flat, and after this the scale factor is added, and the time is fixed with lapse equal to 1, and this is not natural in terms of geometrical embedding, because we are in a Lorentzian manifold. So we need to use dynamical embedding instead of the statical embedding. Well, as you know, we have two geometrical perspectives: the intrinsic, used in Riemannian geometry and pseudo-Riemannian geometry, and the classical extrinsic perspective used in, for example, in 3 dimensions, but also is valid for Lorentzian and Riemannian manifolds. And the idea is to compare our vision of the universe with the geometrical approach to the dynamical embedding of Lorentzian manifolds. The idea is to test some easy manifolds, for example, the hypercone with positive spatial section, the equivalent for the negative spatial curvature, and the flat. And using that the space-time is a dynamical system, so we can apply Euler-Lagrange equations to test analytically how is the behavior. And using the moving reference frames from observers, the metric, the spatial section, is suffering an inhomogeneity, a radial inhomogeneity. This is fictitious. This is from the point of view of the observer, and this radial inhomogeneity can be assimilated within a flat homogeneous space as an acceleration. So Using adequate stratigraphic projection, the manifold, the space-time manifold, can be apparent, infinite, and accelerated. So, with this approach of embedding the hypercon with positive, negative, or flat, we obtain an alternative metric to the Feynman-Lemaitre-Robinson-Walker that has the same spatial section, but the scale factor is linear with linear expansion, and we have two additional terms: the shift and the lapse. With a lapse and shift, if we change the coordinates, we obtain a radial inhomogeneity metric spatially, but locally for each point, this is homogeneous, and the resulting rich scalar is this one. And taking, for example, positive curvature, the rich scalar or our positive curved spacetime is the same that the standard model when it is flat and linear expanding. So our model of spherical expanding hyperspheres are equivalent to the flat standard model with linear expansion. So this is the Méliès model. And applying the Lagrangian formalism and the Hamiltonian equations of and now with the Misner formalism, we obtain that our manifold is only consistent with positive curvature. That is an three-sphere expanding at like speed, and the equivalent density, taking into account the rich scalar, is exactly the critical density. And also this is, as popularly mentioned before, as a black hole, that the escape speed is the light speed. So is a very nice coincidence, and is the only one, the unique solution from the Hamiltonian equations. And comparing with observations, the luminosity distance is constrains the model in the same statistical level than the standard model, and is better than the flat Quastin model and the Milner Quastin model. Comparing to the angular diameters is similar to the standard model. Also for the cosmic chronometers, the results of the Hubble parameter are similar, but with two perspectives, the intrinsic and the extrinsic, because the hyperconical model can be analyzed in extrinsic view, in which the Hubble parameter is just the inverse of the edge of the universe. Intrinsically is simulated and visual acceleration. And applying the perturbation theory, it's possible to apply also the fictitious acceleration at galactic scale, and is assimilated as a Milgrom-Mean acceleration. So the MOND behavior can be recovered with this fictitious acceleration, like the Coriolis acceleration in the atmosphere. And this acceleration, without using observation, is predicted to be very similar to the standard model dependent observation, and with two different values: at local and at global So we can simulate and Hubble tension according to purely geometric techniques, obtain a Hubble that is the inverse of the age of the universe, will intrinsically the prediction of the Hubble parameter is very similar to the Lambda-CDM dependent observation. As conclusions, we have two geometrical perspectives, an homogeneous hypercone expanding to the at light speed is assimilated as a projected radial inhomogeneity that is apparently accelerated flat metric, like the Melias metrics. And these fictitious accelerations is assimilable to dark matter and dark energy, predicting specific values, apparent values, and also in galaxies and galaxy curve rotation. And possible explanation of the Hubble tension with difference in the local and global scales. I don't know if the local void is an apparent of current time, because the differences in distance is also in time. So maybe it's linked. I don't know. I'm not sure. And an explanation for the critical density and for the galactic. I'll also summarizing that is as two perspectives, modeling the most promising models as alternative of the standard model. This is all from my side. I think you are mute.
Yep, I was indeed muted. So it seems that Tindrell already has a question.
Can you go to slide 11 with the different table of the different values of the H0?
Yes. Can you see?
No, you've stopped.
It's not. Okay. It's not sharing. Okay. One moment. Yes.
Yeah, exactly.
The three parameters are our model, and the second part of the table is predicted for the standard.
Predicted based on the model, I see. So what I was wondering is like the local value is about 74. I don't see that in this table, but can you, how do you explain, the race observations of supernovae in the local H0 basically?
Yes. Our local prediction for dark energy is 0.67.
Yeah, but for the H0.
Dark matter plus. Yes.
No, that's interesting. So the omega m should be exactly 1/3, and omega lambda is 2/3, which is quite reasonable. But what about for the H0?
So, sorry, can you repeat the question? Is about the?
It's about the last line of this table, right?
The last line. The last line is a prediction for the Hubble, and the previous one is the prediction for the time. The comparison with the H0 universe and the Hubble time within the intrinsic viewpoint.
Yeah, but okay. So the age of the universe is a different issue, which I haven't answered out yet. But what I was asking about is, how do you explain the high local value of H0 observationally? So that is it's about 74, right? If you were to do a local measurement.
Okay. Do you mean about this habit? Yes, because it depends of the technique. This local value is from Lambda-CDM.
Hang on, I thought you said just now that all the values were predicted based on epsilon, delta, and alpha?
The observation with purely geometrical techniques is just the inverse of time. So our prediction is this one. One moment.
Yeah.
I cannot put too much objects cycle. Okay, so our prediction is 73 for local measurements within the extrinsic viewpoint. That is purely geometrical techniques as laddering of supernovae compared to the for example one moment. No, our prediction is this one, and this is the observation from Rees. Sorry, from Rees et al.
So you're in agreement with that?
73. Yes, and our prediction based on the age of very low metal stars is 73 with instantly, but using the edge universe from Lambda-CDM is 72. So we distinguish between geometrical techniques and observation depends of the light.
Yes, sure.
The light features.
Just one quick thing I wanted to ask: how exactly is this FT defined?
Defined what? Sorry.
FT, the second last line. How exactly is that defined?
FT, yes. FT is the quotient between the predicted time and the Hubble time.
So it's the age of the universe multiplied by h naught.
Yes. Yeah, exactly. This is this.
Just one quick question. How old? Okay, so the universe is basically how old exactly is this? So it's like 4% less than the inverse of h naught. Is that what you're saying?
Yes, I see that we can reproduce the observation of Planck according to this fictitious acceleration. Without
Planck is an observation. The Planck doesn't directly tell you the age of the universe. What I was saying is, like, do you get an age between 13.5 and 14 gigayear? Is that correct? Because because you can't use Planck to determine the age of the universe. You have to do that from like stellar stars or globular clusters, right? But I think you're consistent with that bound, right? That
is this is from the integral. One moment.
Yeah, you'd have to do some sort of integration to find the age of the universe, right? But it seems like it would be
the definition of the with.
Yeah.
Okay, more questions?
So I was just wondering, like, if you haven't figured it out now, that's fine. But I was just wondering, like, so you get an age between like 13.5 and 14 gigayear, right? If you with your cosmology, right?
Yes.
Okay, then it should be reasonable given like non-cosmological constraints on the age of the universe. That's all I wanted to ask for now.
This only is predicting the factor, not the exact value of the age.
Yeah, but obviously, if you were to multiply the factor by, you were to do FT divided by h naught, you could. I would suggest like maybe adding another row, which is like the predicted age of the universe in gigayear.
Of course, this is independent of the time. We always predict that the apparent dark energy is 0.7.
No, I understand.
0.70. And also always we predict this factor, and so this is from the coincidences of the linear expansion, the synchronicity problem. So
you mean the fact that
to predict.
So you mean the fact that the expansion history is very close to linear?
Yes.
Yeah. Okay.
So always we have this problem is if the synchronicity problem is true, that always is apparently linear, we can predict this one. The difference of 4 is due to the assimilation of the fictitious acceleration from the radial inhomogeneity, of the moving observers, and produce an apparent the differences in the past from this distorting curvature from each observer, but it's fictitious. So each observer observes the same phenomenon of apparent acceleration in the past.
I think Morris had a question. Maybe
Yes.
that can be the next one.
Yeah, I have maybe two questions, but they're all related. What do you predict for the future state of the universe? Theoretically, this is relevant because in Lambda-CDM, as you know, that's a stable de Sitter state. Do you predict the same?
The prediction is like this: is linear. So the values expected for apparent dark energy and dark matter will be the same in the future. The differences are in the local structures, but in this case we did not simulate the local structures, but I think it's possible. So the prediction of the universe is a cosmic universe with always expanding, always expansion, and is easy. And I don't know if is the answer for your question.
Because well, you're also sketching linear expansion, and of course for linear expansion, the deceleration parameter will be 0, and that's certainly not supported by the data.
Yeah. Yes, because
it's in the wrong.
From the extrinsic viewpoint. The extrinsic viewpoint is linear and acceleration 0. But according to the intrinsic viewpoint, there is an fictitious acceleration. The dynamical embedding is due to the moving reference frames. The observer is also expanding with the universe. So luminosity distance is not like this. It's not like the extrinsic viewpoint. We are suffering an radial inhomogeneity in the lapse and the shift terms of the metric. And this inhomogeneity is very similar, is exactly equal to an apparent acceleration. So the acceleration observed by the co-moving observers is fictitious according to the dynamical embedding. Right?
Well, fine, but what would the observer see then if the observer measures Q0?
Yes. So we need to distinguish between directly observations and indirect observations. The direct observations are with purely geometric techniques. For example, the laddering of supernova stars, and the directly evolution of the clusters. But the luminosity distance and other measurements of the light are affected by this fictitious acceleration, because light is moving on the basics of this one. So observations based on light are not valid for view the extrinsic viewpoint. But the evolution, the cosmic timeline, yes, cosmic timeline will be always linear. That is the synchronicity problem. And the age of the galaxies, the age of the evolution of the structures will be also linear. So we can explain the tensions of the gordo, of the bigger structures, thanks to this linear expansion and the MOND behavior inherited from this fictitious acceleration. So it's possible to falsify this model according to the cosmic timeline that will be specifically the inverse of time, or inverse of age of the universe.
Thank you.
Well, it would be nice if you can give a number for Q0 that, you know, the observer would measure, say, based on supernovae.
Mm-hmm. And you can read this paper. Yes. More questions?
Yeah. I think Pavel also has a question.
Yes. You mentioned that this approach leads to a MOND-like behavior, right? So I imagine you are probably thinking that it will be flat rotation curves, right? That's interesting. Down to which scale would you, would open star clusters look Mondian in this approach? So on a scale of a parsec, you think?
I not check every details, but the scale is shown here in the rate of escape velocity and Hubble rate, Hubble speed, and the empty universe is in this region, and the black holes, for example, is in this asymptotic, in this parameter 0.5. So all observations we analyze is between, and we need to check specifically how is happening in your region. But the idea is that the phenomenology depends only the acceleration, not from the scale, because it's a problem of dynamical systems, of the velocities. It's not a problem of space, it's a problem of the rate of speech. So we need to focus on the dynamical and not in the scale, in my opinion.
Well, sure, MOND is an issue of acceleration, I agree, but we see MOND effects in open star clusters, and the question is whether you would have to also show that would be possible in this formulation, right?
Yes.
So
I think we can check in the future. Yes, thank you.
Sure. Mm-hmm. Great. Thanks.
Yeah, thanks. I think Renee also has another question.
So related to this, did I understand correctly on this slide that gamma m over pi would, for a very small system with a low ratio of escape velocity to So would star clusters be on the left of this plot then, at a very low ratio of V over V8?
Yes.
Okay, so
Yes.
that means
so
that
this is the Milbronian acceleration is not constant in this model. Depends of the scale of the dynamical scales. That is.
So what you're saying is that gamma m over pi would be about 0.35?
Yes, for very the empty universe is 0.33, and for black holes is 0.5. This, so the Milbronian acceleration is 0 for black holes.
But at the yes, at the right end, because gamma m would be half pi.
So a star cluster being about a parsec large. On the parsec, the Hubble rate is extremely small, right?
Yeah.
And so the escape speed is also small, but that's around maybe kilometers per second. So I think you would be on the right.
But the VE is much lower than VH though, because the Hubble rate is oh sorry, no, it's the other way around.
Yeah, but the Hubble rate is on that scale, right? So the Hubble VH...
Hubble rate on that scale is very tiny, actually.
Yeah, exactly.
So I have a problem because our theory predicts the gray line.
Yes, okay.
And the observed one is the blue. So I don't know why is this difference, but the behavior is very similar. So maybe we need to review the theory in the future, but we are glad because it's possible to adjust the theoretical one to the empirical to obtain the observation. But it's a curiosity why we predict without observations this behavior for black holes 0.5 and the smallest scale galaxies is not exactly passing throughout this gray line, but we will check in the future. Yes.
So my question is actually not related to this. What I was asking is for the galaxy scales regarding the A0 parameter or the effective value of A0 that you predict, which I guess is
galaxy scale is this one, and cluster I think is this one.
Okay, so at the galaxy scale in like meters per second squared, how much are you predicting for the value of A0?
We need to check exactly if you want after this talk.
Okay, fair enough. But what another thing I wanted to ask is like regarding the time evolution of A0. Did I understand correctly that that the A0 will be proportional to 1 over A in the model? It will be inversely proportional to the scale factor. Is that right?
Yes, the scale factor. But we need to. Yes, one moment here. No. Here, but important thing.
Yeah.
This is a metric with lapse and shift. So if we include this shift and lapse in only dependent spatial and time, so that is removing this part, the linear expansion is appearing as an fictitious acceleration. So it's a linear expansion in terms of extrinsic viewpoint, but assimilating this in radial homogeneity is pseudo-accelerating.
No, but I meant like if you think about an observer at low redshift who's looking at a galaxy at redshift 1, then so you can use rotation curves to try and get like constraints on the value of A0 at that epoch, right? And typically that implies that A0 shouldn't have risen faster than A to the -3 halves as you go back into the past. But so if you're predicting a rise going as A to the -1, that should be reasonable.
Yes, and the problem is the information that arrives from light.
Yes.
Because it's distorted. So it's a problem. We need to separate the information information from the light and information from the phenomenon, from the cosmic timeline.
Yeah, but I think you already explained that like the overall age of the universe in your model is more or less reasonable. So.
Yes. Yes, thank you. More questions? No?
So if there are no more questions, maybe we could just do the break now if there are no more questions.
Yes.
Okay,
yes, thank you very much.
So yeah, I guess see you all in 1 hour.
Yes.
1 hour. Yes. Perfect.
Thanks.
Thank you.
Okay, so see you.
Recording stopped.
Yeah, so see you all after 1 hour. We have a break for 1 hour. So let's meet at later on 1 hour, and we have 4 talks. So see you there.